What is the specific problem that the proposed method aims to solve in the context of large language models, LLMs?
The specific problem that the proposed method aims to solve in the context of large language models, LLMs, is how to improve the quality of an LLM by enhancing the quality of its pre-training data through data pruning based on sample perplexity. The method focuses on selecting a high-quality subset of a larger dataset to train on by using perplexity as a metric to determine the difficulty of each sample. By intelligently pruning the dataset based on perplexity scores calculated by a small reference model, the goal is to enhance the downstream performance of the final LLM while reducing training costs and steps. The method aims to address the challenge of efficiently improving LLM performance by selecting the most relevant and high-quality data samples for pretraining, thereby optimizing the learning process and enhancing the overall quality of the language model.
How does the proposed method of data pruning based on sample perplexity work? Please illustrate the process step by step.
The proposed method of data pruning based on sample perplexity works by first training a reference model on a subset of the pre-training dataset. This reference model calculates the perplexity of each sample in the final model's training split. The dataset is then pruned based on a selection rate R_S, where samples are selected according to their perplexity levels. There are 3 selection criteria: low, medium, and high. In low selection, samples with the lowest perplexity are chosen. In medium selection, samples close to the median perplexity are selected. In high selection, samples with the highest perplexity are chosen. After pruning, a final model is trained on the pruned dataset using the standard next token prediction objective. This process allows for the selection of high-quality samples based on their perplexity levels, leading to improved downstream performance of the final model. The method emphasizes the importance of downstream model quality evaluation, explores different dataset domain compositions, and analyzes pruning in non-standard training regimes.
What are the main theoretical or practical benefits of using perplexity-based data pruning compared to other techniques?
The main theoretical and practical benefits of using perplexity-based data pruning compared to other techniques include 1. Improved downstream performance. Perplexity-based data pruning has been shown to significantly improve the final model's downstream performance. By selecting samples based on perplexity levels, the resulting pruned dataset leads to better performance on downstream tasks compared to models trained on unpruned data. 2. Enhanced training efficiency. Perplexity-based data pruning not only improves final model performance, but also enables models to achieve the same downstream performance in fewer training steps. This means that training on pruned data can lead to faster learning and more efficient model training. 3. Sensitive to dataset composition. Perplexity-based data pruning techniques are highly sensitive to the domain composition of the dataset. Different dataset compositions may require different pruning strategies, and perplexity-based pruning allows for tailored data selection based on the dataset's characteristics. 4. Non-standard training regimes. Perplexity-based data pruning has been evaluated in non-standard training regimes such as overtraining and data-constrained training. It has been shown to still provide gains in performance in these scenarios, showcasing its versatility and effectiveness across different training settings. 5. Direct evaluation on downstream benchmarks. Unlike traditional metrics like test set perplexity, which may not accurately reflect model quality, after data pruning interventions, perplexity-based data pruning allows for direct evaluation on downstream benchmarks. This ensures that the impact of data pruning techniques is assessed based on actual task performance rather than proxy metrics. 6. Complementary to existing techniques. Perplexity-based data pruning complements existing rules-based and n-gram perplexity pruning methods by providing a model-based approach to estimating data quality. It can be used in conjunction with other techniques to further enhance the quality of pre-training data. 7. Ability to handle large datasets. Perplexity-based data pruning can effectively handle large datasets by intelligently selecting high-quality samples based on their perplexity levels. This allows for efficient data pruning, even in scenarios where the dataset size is substantial. 8. Flexibility in selection criteria. Perplexity-based data pruning offers flexibility in selecting samples based on low, medium, or high perplexity levels. This adaptability allows for fine-tuning the pruning process based on specific dataset requirements and characteristics. 9. Insight into data distribution. By analyzing the distribution of reference model perplexities and the effect of pruning on domain composition, perplexity-based data pruning provides insights into how data quality impacts model performance and dataset characteristics. 10. Overall performance gains. Perplexity-based data pruning has consistently shown to outperform baseline models across different datasets and model sizes, leading to improved overall performance and efficiency in LLM pretraining.
How were the experiments conducted to validate the effectiveness of the proposed method?
The experiments to validate the effectiveness of the proposed method were conducted by training a reference model on a random subset of the pretraining dataset and evaluating its perplexity on each sample in the dataset. The dataset was then pruned to include samples within a certain range of perplexities, low, medium, or high selection criteria. After pruning, a final model was trained on the pruned dataset using the standard next token prediction objective. The experiments involved considering different pre-training dataset domain compositions, evaluating perplexity-based data pruning in overtrained and data-constrained regimes, and comparing downstream model quality based on downstream evaluation benchmarks rather than just upstream metrics like perplexity on the test split of the pre-training dataset. The experiments demonstrated that models pre-trained on the perplexity-pruned version of the dataset significantly outperformed baseline models trained on the original datasets without pruning, leading to significant gains in downstream performance and efficiency.
What were the key results achieved with perplexity-based data pruning in terms of downstream model performance improvement?
The key results achieved with perplexity-based data pruning in terms of downstream model performance improvement include significant gains in the final model's downstream performance, with improvements of 1.89 and 1.51 for 1 billion parameter models and 2.04 and 0.59 for 3 billion parameter models on the Pile and DOLMA datasets respectively. These results indicate that training on the data selected by a small reference model based on perplexity leads to substantial downstream performance improvements. Additionally, the study found that models pre-trained on the perplexity-pruned version of the dataset consistently outperformed baseline models trained on the original datasets without pruning, across all datasets and model sizes. The research demonstrated that perplexity-based data pruning not only enhances downstream performance, but also leads to increased training efficiency, enabling models to achieve the same downstream performance with fewer pre-training steps. Furthermore, the study explored the impact of perplexity-based data pruning in non-standard training regimes, such as overtraining and data-constrained training, providing insights into the effectiveness of this pruning technique across different scenarios.
What are the limitations or drawbacks mentioned in the paper regarding the application of perplexity-based data pruning?
The limitations or drawbacks mentioned in the paper regarding the application of perplexity-based data pruning include the potential misleading nature of test set perplexity as a metric for evaluating the efficacy of data pruning techniques. The paper highlights that interventions resulting in significantly higher test set perplexity can still lead to better performance on downstream tasks, indicating that test set perplexity may not always be a reliable evaluation metric for data pruning work. Additionally, the paper discusses how models trained on perplexity-pruned data may become biased estimators of the original data distribution, suggesting that performance on the original data distribution may not accurately reflect model quality after pruning. Furthermore, the paper notes that while perplexity-based data pruning can lead to improvements in downstream performance, there may be scenarios where the gain from perplexity-pruned data decreases, such as in the case of overtraining models, where the relative increase in downstream improvement over the baseline diminishes.